Good day, students. Welcome to Mathgotserved.com. In this clip, we're going to be going over problems 25 to 27 of the Geometry Common Core New York Regents exam for June 2015. All right, let's take a look at problem 25. It reads, use a compass and a straight edge to construct an inscribed square in circle T. In the circle T shown below with all construction marks. Now, one thing you want to note is that the diagonals of squares are perpendicular bisectors of each other, okay? And if you do not know what an inscribed square is, let me give you a sketch just to give you a visual of what an inscribed square is. An inscribed square is basically a square constructed in such a way that the vertices intersect the circle. Okay, so let me show you an inscribed square. So there goes the circle, and you basically want to inscribe a square in it. So the four vertices has to touch the circle. So there goes an inscribed square. So what I stated earlier is that the diagonals are perpendicular bisectors of each other. So this diagonal, that's one diagonal, which is equal to the diameter of the circle, is a perpendicular bisector of this diagonal right here. So what do I mean by perpendicular bisector? This is 90 degrees. This side is congruent to that side, and this side is also congruent to that side. So using SAS, you know for a certainty that all the four sides are congruent to one another, okay? So that's what we're going to do. So let's look at the steps. We'll construct a diameter, which is equivalent to one of the diagonals. We'll then construct the perpendicular bisector of that diameter, which is going to be the second diagonal of the square. Then just connect the endpoints of the diagonal in such a way that it intersects the circle, and there goes your square. Okay? All right, let's go ahead and do it. So first things first, let's draw. You just use your straight edge. I'm using electronic tools here, so bear with me. You just place your ruler down and draw a segment that intersects with the circle and also goes through the midpoint. Okay, so that will be one of the diagonals. Okay, now we have that down. Now what we're going to do next is we're going to construct the perpendicular bisector of this diagonal. This diagonal is one of the diagonals of the square. Okay, so let's go ahead and do that. So I have my compass here. You know how to construct perpendicular bisectors, right? So you place the endpoint of your compass, your protractor on the intersection of the diameter and the circle, and then you're gonna create an arc. So I'm going to extend my compass in such a way that the arc goes across where I anticipate my second diagonal to be. So I expect my second diagonal, or the perpendicular bisector, to be somewhere here. So make sure that your compass is extended beyond that measure, okay? So check this out. When I move my compass, let me bring it down a bit. This is a little bit complicated to use. When I move my compass, I want to make sure that the arc intersects where I anticipate the diagonal to be somewhere outside the circle. Okay, so look at that, something like that. I think that should work. Okay, so I'm going to go ahead and make an arc. I wonder why the color is red. That's fine. All right, so there goes my first arc right there. And then I will make another one on the bottom. This is your basic bisection of a segment procedure that we're doing here. Create another arc. Okay. All right, now what are we going to do next? We're simply going to place the tip of this compass right here and create another pair of arcs, and then the point of intersection of the two arcs are going to be the points that will be used to define my perpendicular bisector. Okay, so just move your compass to this end right here, and then I'm going to make my arcs again. So it's upside down, just make an arc right here, and then scroll to the bottom, and then make another arc right here. Okay, so now we can draw our perpendicular bisector. It's basically a segment that goes through these 2 points of intersection. Okay, so we're gonna have, I'm gonna go from here to here. Now, if you're doing this with a paper and a ruler, you don't have to extend your segment beyond the circle, okay? Because this is what we want. We want the portion of the segment that ends right here, okay, here and there. Now, I just need the diameter portion of this entire segment. How are we going to create our square? We just simply connect this endpoint right here to that endpoint, this endpoint right here to this endpoint right here. We're just looking for the diameter, that's all, to that endpoint, and this endpoint right here to that endpoint. Please be sure to leave all your markings on the paper so that your teacher can know exactly what you did to come up with your result. Okay, so this side is congruent to that side. Those are the radii, okay? And then this segment is congruent to this segment, and this is 90 degrees. All of them are all 90 degrees. So basically using SAS, we know that our 4 triangles are congruent. The 4 hypotenuse are congruent, so that tells me it's a square, and is also inscribed in the circle, so that's exactly what we want. All right, let's take a look at number 26. It says the diagram below shows parallelogram LMNO with diagonal LN, and so we have a parallelogram right here. Measure of angle M is 118, and measure of angle LNO is 22 degrees. So the question is, explain why the measure of angle MLO is 40 degrees. Now, one thing you want to remember is that opposite angles of a parallelogram are congruent. Okay, so let me show that to you visually. This angle right here is congruent to that angle, and angle M, guess what? Angle M is congruent to angle O. All right. Steps are as follows. We're going to use the properties of a parallelogram to find angle O, or angle NOL, and then we'll use the triangle angle sum theorem with this angle, measure of angle LNO, to find the measure of angle NLO. Okay, 1L to find LNO. Okay, now let's go ahead and do it. So first thing we're going to state is that we know that since opposite angles of a parallelogram are congruent, then what? That follows that angle O is congruent to angle M. So if the measure of angle M is equal to 118 degrees, then what? Then the measure of angle O is the same thing, since they are opposite angles and they are congruent. Now we're done with step number 1. So now we know what angle O is. We're now going to use the triangle angle sum theorem to find the measure of angle NLO. Okay? So let's go ahead and write it down. So from the triangle angle sum theorem, let's write it completely, triangle angle sum theorem. We know, what do we know? We know that that angle O, the measure of angle O, plus the measure of angle L and O, plus the measure of angle NLO is equal to, well, let's take a look at it, make sure I wrote it correctly. So measure of angle O plus measure of angle LNO plus measure of angle NLO is equal to 180 degrees. Okay? All right. We know that the measure of angle O is 118. 118 plus the measure of angle LNO is 22 degrees. That's given. Plus the measure of angle NLO has to be 180 degrees. Okay, so let's get this by itself. Combine these two together, we have 140 degrees plus the measure of angle NLO is equal to 180 degrees. Subtract 140 from both sides. And then you get measure of angle NLO. The measure of angle NLO is equal to 40 degrees. Okay? So that's that. All right, let's take a look at problem 27. It says the coordinates of endpoints of segment AB are -6, -5. B is 4, 0. Point P is on AB. Determine and state the coordinates of point P such that the ratio of AP to PB is 2 to 3. The use of the set of axes below is optional, so you could use a set of axes if you want. It's not really important. Okay? So let's go over the reminder real quick. A real quick reminder is that if a segment is partitioned using the ratio A to B, then the slope of the segment is also partitioned in the same ratio. All right, so the steps we're going to do are as follows. We're going to write down the formula to find the coordinates of the partition segment. We're then going to find the constant of partition K. And then we're going to label our coordinates and plug them into the formula along with K to find the coordinates of point P. So this is the formula we are going to be using to solve this problem. So it says if a segment AB from A, x1, y1 to B, x2, y2 is partitioned by P, xp, yp, with a ratio AP to PB equals A to B, then the x-coordinate of the points that's partitioned using this ratio is x1 plus k times the run. We know the run is x2 minus x1. And the y-coordinate of the point of partition is y1 plus k times the rise. Okay, and we know that the rise is y2 minus y1. So let me just give you a visual. It's not necessary, but I just want to give you a visual of what we're dealing with. And then we'll just use a formula. It's pretty straightforward. You just need to know what your different components are. So let's sketch the 2 points, the segment, and I'll show you the whole idea of partitioning. So A is 1, 2, 3, 4, 5, 6, -6, 1, 2, 3, 4, 5. That's point A. And then B is 4, 0, 1, 2, 3, 4, 0. That's point B. There goes your segment. Now, there is a point somewhere. We're partitioning it using this ratio 2 to 3. Okay? So let's pick the point somewhere. So let's say the point is somewhere here. Okay, so that's point P. All right, so what are the coordinates of this point? Point P is xp, yp. What are the coordinates of that point? That is what we're looking for. This is x2, y2, and this is x1, y1. Okay, this is just a visual to help you see that we're partitioning this segment in the ratio 2 to 3. Okay, all right, so let's go ahead and get started. First of all, we want to write down our formula. That's what's going to guide us. xp is x1, your starting point, plus adjusting your run by the constant for your partition. So the run is x2 minus x1. So we are shrinking the run by this constant, all right, the ratio 2 to 3. And then how about the y coordinate of our partition P? Same procedure, y1 plus, we're going to shrink our rise by that ratio. Okay, our rise is y2 minus y1. What on earth is k? Well, k is basically a divided by a plus b. All right, because if you have, so we have the ratio 2 to 3. So basically what we're doing is looking at the first value as a, and this second value is b. All right, so from a to p, we're looking at a 2 piece of the ratio. So that's why we're going to have 2 over 2 plus 3. Okay, so that's going to be 2/5. That's how much we're going to shrink our rise and our run by to get to this point. Okay, so that's how you find your P, the constant for your partition, is you just put A, the smaller one, divided by the sum of the two of them, as long as you're starting from here. If you're starting from there, then you have to use 3, okay, to get to this point. So there goes K, excellent. Now, what is x1? x1 is negative 6. x1, x2. x2 is, what is x2? 4. x2 is 4. y1 is negative 5. y2 is 0. Okay, don't forget, your first point is x1, y1, x1, y1. Your second point is x2, y2. It's always good to label your points so you don't make any mistakes when you're substituting them into the formula. All right, so hopefully I didn't mess anything up here. So let's go ahead and plug them into the formula. So we're going to have the x-coordinate of our pointer partition is x1 is, we already know what x1 is, right? x1 is negative 6 plus k, the constant for partitioning, is 2 over 5 times x2, 4 minus x1 is negative 6. Okay, simplify that, negative 6 plus 2/5. Minus times minus, you slash and dash, which makes that a plus. 2/5 of 10. All right, and then you have negative 6 plus 5 goes here 1, 5 goes here twice, 2 times 2 is 4. Negative 6 plus 4 is negative 2. So that's the x-coordinate of your partition. Y of p is what? It's y1, which is 0, plus, actually y1 is not 0. y1 is negative 5. Negative 5 plus rise over run, no, plus your k for your partition, k over p. We're taking this fractional piece of your rise, y2 minus y1. y2 is 0 minus y1, which is negative 5. Okay, so minus times minus, you slash and dash. And then you have negative 5 plus 2 over 5. This negative 5 becomes positive times 5. 5 goes here 1, 5 goes here 1. You're left with negative 5 plus 2, which is negative 3. So your final answer, so the coordinates of P, the coordinates of P is what? Negative 2 for the x and negative 3 for the y. Okay, so there goes your final answer. Thanks so much for taking the time to watch this presentation. Really appreciate it. If you found this tutorial beneficial to you, please give us a thumbs up. We'll appreciate your positive feedback, and do share it with your friends so that they can also benefit from it. If you have any questions about this tutorial or any questions in the Geometry Common Core Regents exam, just place your questions in the comment section below, and we'll be glad to address it as soon as possible. Do not forget to subscribe to our channel for updates to the remainder of this review series, and also test out your skills in our interactive practice test here. And also don't forget to visit our website, mathgotserved.com, for access to other great math tutorials. Thanks again for watching, and have